2.
All right. We doing this? That looks good?
Centered.
Beautiful. Okay. Gosh, I tried to figure out how to make it so that I could see my notes without you guys being able to see my notes.
Don't mirror.
Well, no, that's the thing. It's not mirroring. It's the technology I'm using for my slides. I think I just have to switch to something else. Whatever. Life goes on. Okay. Well, gosh.
Oh, why don't you introduce yourself?
Oh, introduce myself. Okay, I'd be happy to do that. So, my name is Blaine Hansen.
Hi, Blaine.
Hi, Blaine. I'll let these gentlemen settle first. What's up, guys?
Hi there. Yeah, sorry about that.
No problem. We've just been shooting the breeze and figuring out how to record
They're
this.
just not used to us starting after this.
Yeah, it's kind of weird. It's a little early for the start time, but you know what? We'll do
I'm
it.
so excited! Okay. Yeah, this is I've recorded myself giving this, in a room by myself, but I haven't done this in front of people yet. So this will be fun. Let's see how it goes. Okay, but yeah, my name is Blaine Hansen. I guess I'm a full stack web dev at a little startup called Market Dial that's located in downtown Salt Lake. And I have been interested, I guess a little bit of my personal story will come into this a tiny bit. I've been interested in Rust for years because it feels like, everything that I write in Python or something is always broken all the time. And so I'm tired of that. And I guess this is kind of the logical conclusion of that journey of realizing, oh wait, everything doesn't have to be broken all the time. And it's not the conclusion. I just found a mountain to climb. But yeah, so I guess the essential idea of this talk is to discuss formal verification, what it even is, kind of the core ideas, explain the core ideas in ways that aren't, really academic and awful, and then talk about this Magmide project that I've been working on that's very early still, but that I hope could make this all practical. Okay. Yeah, let's just get after it. So I won't spend much time on this because we all already know this is true, but it's good to have in the back of our minds. It's just that software is extremely important and it's also extremely broken. There's these ways I was coming up with of ways that software being broken causes big problems for people. And I found these 2 reports that are just adding a little more rigor to this idea. I think the CISQ stands for Software. Oh no, Consortium for Information. I can't remember. For something software quality is basically what that is. But they released a report in 2020 for just the cost of poor software quality in the U.S. And they were stating larger numbers. They were kind of about lots of different kinds of poor software quality problems. But these 2 subset numbers interested me. They estimate it costs about $1.56 trillion a year in just operational failures, things breaking and that causing slowdowns or lost value in other parts of society. And then $1.31 trillion in technical debt. And importantly, it's not technical debt, all technical debt. All of us have technical debt in all of our systems. It's all over the place. This is technical debt in critical systems, systems that underpin some sort of important societal function. That they are basically saying, this has to be paid down. This isn't optional, right? And then this McAfee report, the hidden costs of cybercrime. Basically, their number is, it's shy of $1 trillion globally of literal monetary loss from cybercrime. And then about 145 billion global spending in cybersecurity. So, we already know this. We work with software. Software's broken all the time. And we see the ways that it hurts things and causes problems and slows us down and slows down human progress generally. So this matters. Software is in our financial systems. It manages our nuclear arsenal. It's extremely important, and it needs to be more correct than it is. So, yeah, this isn't necessary. It's not mandatory. It's avoidable. It's not easy to avoid, but it is possible. So that's what formal verification is. It's a very academic discipline at this point of people figuring out how to use the tools of formal logic, right, mathematical proof, to basically guarantee with the same amount of certainty that a piece of software is correct, that they know that 1 + 1 = 2 is correct, that is true. And I first got started on this kind of journey of being interested in this stuff and kind of going down the road of learning about it with this Quantum Magazine article. Hacker proof of code confirmed. And basically, in this article, they just basically tell the story of, I think this was in 2015, a DARPA-funded team of, they're all professors, they're all people from, probably a lot of them you've heard of, like Kathleen Fisher is one of them, anyway. But this DARPA-funded team of researchers was basically given the task to create control plane software for, or maybe control plane software is not the right term, but the control software for a quadcopter, a military quadcopter. And then they gave a red team, of elite hackers, basically the kind of security researchers that can take over a Jeep with Bluetooth or make an ATM, give them as much money as they want, or these people who are demonstrating insane vulnerabilities in software systems all the time. They actually gave them access to a part of this quadcopter and said, okay, take it over. Hijack the quadcopter. And they weren't able to get anywhere. It's not even they couldn't achieve that goal, they could make zero progress. And the way that's possible is that this software that these researchers had written was, again, it was logically proven. They had mathematical certainty that at least the kind of security breaches that they had specified it to be secure against, it was absolutely secure against, right? Things like buffer overflows or weird integer overflow exploits or things like that. So it was mathematically impossible to take it over in those ways. So, I mean, the reason I think that project, I'm hinting at the fact that the tools and the techniques they were literally using can't just be picked up by normal practitioners. They're extremely academic, and they're also extremely narrow, and they were very fitted to the thing they were doing, and they had tons of funding, right? It's kind of this ongoing university DARPA initiative. And the hope of Magmide, we'll get more into this later, the hope of this language that I'm working on, again, it's very early, is to make all of this practical, right? To kind of build a language that is kind of the rust of formal verification. And actually that itself will underpin Rust. I'll talk more about that later. So whenever I talk to people about this, there's a certain amount of skepticism of, there's no way, people, or you think engineers are going to write proofs, or how does this work? How is this even possible? And so the first thing, the big chunk of the middle of this talk, I wanted to talk about the core ideas of formal verification, how this idea works, and how you can have code and proofs be the same thing. And these are the three ideas we're basically going to talk about. And then we'll talk about, Magmide specific design a little bit. Okay, so the first thing here, this is a Rust function. This is a really lame function. And we're talking about this function to illustrate the problem, or maybe a deficiency in normal type systems, ones that we're familiar with, and to understand, therefore, how dependent types are cool and what they are. So, is1, lame function, takes in an argument n, which is an unsigned 64-bit integer, and returns a Boolean. And the body of this function just checks if this n is equal to 1. Pretty lame, but whatever. And the type of this function, is U60, a tuple of a U64, and is transformed, right, in the kind of type theoretical sense into a Boolean. The problem is that type we just saw, there's very little information in this type. We just know that we put in some unsigned 64-bit integer, and we get out some Boolean, and we have no information about what these things mean, if they have a relationship to each other. It's very opaque. And to really hammer that home, all of these functions have the exact same type, and they do very, very different things. Right? One checking for 0, one returning true and always, one returning false always. So this, I actually won't go over this function yet. The basic idea of a dependent type is that in most type systems, types can only reference other types, right? You can have generic types, for example, that reference another type as one of their parameters, basically. But a dependent type is allowed, within type, you can reference a value. Or, the type can depend on a value. That's why they're called dependent types. And this is a function written in a language called Coq, C-O-Q, which is the French word for rooster. And it's a terrible name, and there's lots of problems with this language. I'll kind of get at this. But basically,
other than the naming itself?
Other than the name, yeah, I promise there's lots of issues with it. It is extremely powerful. We'll talk about why. But, this is basically is1. It's the same function we were doing before. But, in this Coke language, I'll explain. This isn't a Coke lesson, but I'm kind of giving a taste, but I'll explain bits of it. But this function has a dependent, its return value is dependently typed. And here's the actual type of this function. The way we read this off is, for all, or for any, right? Basically, for any n, for any specific n, which is a natural number, that's kind of like an unsigned integer. Coke models numbers differently. That's where I'm not going to get caught up on that difference. But for any n, we return one of these things. And basically, this can be read as we return a b, which is a Boolean, such that b is true if and only if, that's what these arrows are, if and only if n is equal to 1. And, that's the core idea here. That's why this is a dependent type, is that it references the input value of the function within it. So instead of just being a Boolean, this is a Boolean that is constrained to only be true in the situation where that n, that specific n, was 1. And then basically this line right here is me kind of telling Coke how to prove this. I'm kind of giving it a tactic that it can use to construct a proof. We'll talk about that in a second. That this all makes sense, and then what I'm doing is consistent.
So,
yeah.
Sort of, at least in this case, encoded all of the logic in the function in the type of the function, and then you repeat the logic of the function in an implementation.
Well, kind of. A little bit. So that's the thing, is this isn't necessarily a smart way to actually write code like this, but it illustrates a point. Right. And oftentimes when people are actually using Coke specifically to do this, the thing they're encoding in the return type is a lot more compact. They maybe will have like a proposition or something they will just kind of pack in there. And the implementation is a lot more complicated. And so the fact that the implementation fulfills this contract is more interesting. This is a really lame example, right? This is really, really lame. But again, it's just kind of serving to illustrate the capability, the thing. It says, yeah, I'm not saying anyone should go write functions like this. But I guess the cool thing about this, or this leads to the idea that type checking and proof checking are the same thing. And basically, the idea of dependent types means that since a type can reference specific values, you can do things like have a piece of data that is a piece of data that represents the idea that one number is less than another, or something like that. This is kind of complicated. Again, I'm not giving a whole lesson about this language. But basically, in order to check that all these things are consistent, all that Coke has to do is run a type checking algorithm and just check that all of the types are consistent with one another, or that the things like values are the same. So as an example, if I made a mistake in this function and I accidentally said, oh, I'm comparing against 0 instead of comparing against 1 like I'm supposed to, then, I'd give this tactic to Coke, and I'd say, oh, use this tactic to kind of figure out how what I'm doing is correct. What it's doing secretly is it's actually constructing code. It's basically code is the thing that proves what I'm doing is correct. But then it would when it type checked that code that was produced by this tactic, it would say, oh, this isn't consistent. This doesn't type check. In order to get it to sign off on this function, I would have to be able to construct a proof that 0 is equal to 1, which is obviously impossible. I can never do that as long as the type checker is correct, right? And so the really crappy kind of parlance, or the language that Coke uses to kind of describe situations like this, is unable to unify 0 and 1 or whatever. So I guess I'm hinting that Coke is not very usable, but this is extremely powerful. And yeah, just being able to kind of let loose a type system that can check that proofs are correct is extremely amazing. It's extremely powerful, even though this example is so lame. So just to kind of give a little bit more of a hint of how this is useful, right, and not to have such a lame example, this is defining a new data type in Coke. They use the inductive keyword to do this. And basically what this does is it is a type that accepts values, right? It's a type that basically is able to take in these natural numbers, and it kind of it returns propositions, right? Logical propositions. I'm, again, not a Coke lesson, not going to get hung up on these details. But this type, basically, is like an enum in Rust. It has two versions. It has two constructors, two variants. And, here's one of the constructors. It's called even_0. But the type of this piece of data, the type of this constructor, is that 0 is even. So I guess that's what's happening here, is that I'm just making a type, and I'm making it so that the rules of this type, the structure of this type, lines up with our rules, or lines up with a way of making assertions about numbers being even. So we have kind of the bottom of the recursion, right? Where at the bottom, 0 is even. We just kind of state that as true. And then we have this even plus 2 constructor that basically, its type is that if I give it any n, any other, any natural number, and I give it a proof that n is 0, or not that it's 0, that it is even, and I can start with this 0 one at the bottom, then it'll give me back a proof, or a piece of data whose type is a proof that number, basically n plus 2 is even. And that's what these S's are. Again, Coke models numbers differently. It's kind of a more like formal logic version of modeling numbers. Again, don't worry about it. But this is really, really cool. Basically, we can kind of encode this idea in a type, and and if we're able to construct values of this type, then we're constructing proofs of numbers being even. So, here's an example. Here we're basically defining a piece of data. And I'm kind of just saying, if at first, the type of this piece of data is that 4 is even. And I haven't just defined what this piece of data is yet, but I'm saying its type is that 4 is even. And then again, I'm using the tactic system here to do this. I'm saying, here, Coke, here's how to figure out how to construct a piece of data that proves that 4 is even. And secret, I guess I didn't put this in the slide. I put it in the slide. It's going to start with even 0, and then it's just going to pass even 0 to this, to even plus 2, to get a proof that 2 is even, and then it'll pass that to itself again to prove that 4 is even. It'll just kind of be this like nested piece of data that goes all the way down to 0. And that's all this repeat constructor thing tells us to do. And here's an even cooler example where this is a recursive function. That's what fixed point means in Coke. And basically, it's called double, and it takes another natural number, and it does some stuff. It does a recursive algorithm that will end up basically multiplying this number by 2. It'll double it. That happens to do that. But then here is another piece of data that I'm making called even double. But the type of this function, or not the type of this function, the type of this piece of data is a function type. It's the type of this piece of data is for all n, right? You can put in any n, a function that accepts any n, and then I can give you from any n a proof that doubling that n is even. So this is just a logical proposition in formal logic, but it's actually a function type in type theory. This is probably the most mind-bending, confusing part of this, is that data and proofs are the same thing, and proof checking and type checking is the same thing. I'm not going to get hung up on that because it's really easy to get. This is the one thing that's kind of actually you can get wrapped around the axle trying to understand. It's the one thing that's kind of difficult, but that's basically all it is. It's just kind of getting over the hump of, oh, that's true, interesting, okay. But again, I'm not actually defining this function. I'm just telling Coke how to figure out how to build this function. But again, the cool thing here is that if this type checks, if basically my tactics do the right thing and they construct a function that has this type, then the Coke proof checker or type checker can make sure that's actually consistent. And all of a sudden, because I've constructed a function that can always take in any natural number and always produce this proof, I've proven with absolute certainty and for the infinite series, right, for the infinite set of natural numbers, that this always is true. So I guess the way I think this is cool to think about is this thing is literally infinitely better than a unit test. Literally infinitely. Because a unit test, all we can do, sorry.
Well, what happened if I passed in a number that was the maximum value that the numeric type could hold?
They're encoding numbers as a kind of recursive linked lists. I mean, it's a different encoding of numbers. So this,
arbitrary length.
Yes, they're arbitrary length
integers.
integers. Exactly, yeah.
They won't have the range limit on it.
At least the model of it in logic, yes.
Okay.
We could model it as bits or something, right? And then say if you give me any 64-bit whatever, I can also prove that. So it's possible to take in something different. And then it's just, well, you give me 64 bits, and so you can't possibly give me more than 64 bits. That's what you're giving me. But yeah, anyway, so where was I? This is infinitely better than a unit test. Oh yeah, because a unit test, all we can do is we can kind of collect a couple of values, or we can randomly generate a bunch of values and run them through the function. We have to actually run the function and check that something's true. And here, the type system is guaranteeing that all values will maintain this property, which, yeah, I don't know. That's really cool. The fact that you get this absolute infinite certainty. So even this example is pretty lame, right? And I mean, even numbers is whatever. But a lot of the stuff that Coq is actually used for in practice is things like defining the type systems of other languages. Just it happens to be really good for that, the way that it's designed. And so you can kind of design the AST, right, the abstract syntax tree of your language, and then you can kind of prove, and then you also define kind of the evaluation rules, how this AST is, changed over time as it computes. And then you can prove with absolute certainty that your type system has certain properties, or that certain things will always happen with certain functions or whatever. Yes.
So you're saying it's used for other languages for their type verification, right?
Or yeah, kind of modeling the language as types in code. Yeah.
I'm just understanding
Somewhat.
more and more about how the different operating systems would work, but basically it would make like a binary that the language would access.
Not exactly. So I guess I'm talking about they will. Have you ever written a parser or have like an abstract syntax tree thing before? Have you ever done something like that?
No, I don't.
Not really.
Self-taught, so I've
Yeah,
heard
yeah.
about that though, where if you just keep going.
Or yeah, it's basically that if you have something like a while loop in Rust, that when Rust actually reads that file, it's going to pack all the ideas of that while loop into data structures, right? So it'd be like a while structure. And that while structure will point, have like one of the things inside of it is an identifier of n that I'm incrementing in the while loop or whatever. So basically code is just data. And you can always, when you parse code, you just kind of build it as, I wish I had slides to talk about this. I didn't anticipate this question. But, since code can just be data, when we're actually dealing with it in a compiler, that's kind of the level that Coq would talk about it. It would talk about it in this abstract, theoretical sense, rather than maybe the literal stuff, the assembly language version of it that's going to run on a computer. Maybe.
And so the idea is that you have this syntax tree. It represents some ideas. A while loop represents some logical concept, and you're able to encode that concept as certain logical assertions that this language can verify are true.
Yeah, I mean, so oftentimes the way this is done is they might have something like one of these types that has a prop, or that returns it it lives in the prop universe, whatever, the proposition universe, and they might use that to encode. Oh, if I have this AST, it will evaluate to this AST in the next step of computation.
Yeah. Would you say that doing this kind of formal verification, one of the weaknesses is almost that it's so separate from whatever your actual implementation? Okay. Yeah.
That's going to be.
That means whatever you're writing here is almost implicitly has whatever assumptions you have.
Yeah. So there's aspects of that I'm gonna get at. Okay. Yeah. I mean, although put a pin in that. I think that's a great thing to delve on a little bit more. Yeah. But aspects of that I'll address in part of this. Yeah. Okay, so like I said, not a Coq lesson. It's pretty complicated. I mean, it's not. I guess that's part of the point of this talk is it's actually not that complicated. Engineers can learn this kind of stuff, but it's explained really terribly. But these resources are pretty good. They're not perfect. They're both still kind of academic, but they're not punishingly academic. They're very get-throughable. I was able to. Software Foundations here is particularly good. So, yeah, so I guess the follow-on question I had when I was learning about this stuff, okay, or I guess I'll just say first, these systems are obviously extremely powerful. They're not just theoretical. So they're being used to do very difficult, important things. These four, I think, the Feit-Thompson theorem is a really complicated theorem in mathematics that was finally able to prove it in Coq. DeepSpec is another academic project where they're verifying things like parts of LLVM, or they're verifying different C compilers or different kind of low-level stuff. High assurance cyber military systems is actually the project we kind of talked about in the Quadcopter magazine article. Project Everest is verifying kind of the protocols, the security protocols, the encryption protocols that underlie the internet. So yeah, I mean, that's amazing. This is really, really cool. And that's my follow-on question. Okay, why doesn't anyone know about this? Why is this so hidden away? Why aren't even, really advanced programmers that I meet, people who are building extremely complicated systems or really important systems, why have they never heard of this? What's going on? I mean, the first most obvious reason is something called research debt. We'll talk about that in a second. But I don't think it's actually the main reason. I think this is the reason, basically, that all these systems, things like Coq, and there's other languages that are like this, and kind of the community in general, is too dogmatic about the pure functional paradigm. I'll get into that too. But first, this idea of research debt. So I did not come up with this. This was coined in a really good blog post by Chris Olah and Sean Carter, basically talking about, well, you know what, this blog post is just really good. I'm just going to read some quotes from it. It's amazing. And these quotes are out of order, but it's really good. There is a trade-off between the energy put into explaining an idea and the energy needed to understand it. On one extreme, the explainer can painstakingly craft a beautiful explanation, leading their audience to understanding without even realizing it could have been difficult. On the other extreme, the explainer can do the absolute minimum and abandon their audience to struggle. This energy is called interpretive labor. This is from a different part of it. He's talking about people climbing the mountain of mathematics, learning all the different things in mathematics. People expect the climb to be hard. It reflects the tremendous progress and cumulative effort that's gone into mathematics. The climb is seen as an intellectual pilgrimage, the labor or rite of passage. But the climb could be massively easier. It's entirely possible to build paths and staircases into these mountains. The climb isn't something to be proud of. The climb isn't progress. The climb is a mountain of debt. The insidious thing about research debt is that it's normal. Everyone takes it for granted and doesn't realize that things could be different. So yeah, it's this idea that academics who are doing incredible, amazing, cutting-edge work, and they're pushing human knowledge forward, but they have extremely poor incentives to properly explain what they're doing and make it so that it can actually escape from academia and be applied. And it makes perfect sense why. An academic's career is based on writing, prestigious papers that are well reviewed by their peers. Their peers that are also on the cutting edge in their exact same very, very narrow research discipline. And so that means that they don't have to do anything to explain their ideas or properly expose them. They just assume shared knowledge, and they say, oh, you guys know what I'm talking about. And as long as their peers think these papers are good, they can get tenure, they can win awards, they'll get referenced, they'll get cited. And that's a really severe societal problem. We need to fix that in general. That's a huge issue because we're wasting all of this amazing work. But I can't solve that. I don't know how to solve that. But I think this formal verification stuff, I think, is possible to pull out. But this is what I actually think is the real reason that a lot of this stuff has not found kind of traction. Both, tooling's bad. Things like Coq are really hard to use. They're poorly designed. They break in lots of random ways, ironically. But it's more that the pure functional paradigm is kind of the de facto of academics. And just to remind anyone, or to tell anyone what the pure functional paradigm is. Basically, in a pure functional paradigm, things like Haskell and Lisp and Scheme, and I think for variants of ML, and Elm is a front-end language that is pure and functional. Basically, in pure and functional languages, they just outlaw the idea of mutation, and therefore side effects. So all data is immutable. You cannot mutate data, period. So if you want to do a computation on a piece of data, you just have to kind of copy pieces from it and make new data. And, that's useful in ways. There's lots of ways that actually yields a cleaner system. It makes the language have the same kind of mathematical cleanliness and purity as pure logic. It's not as powerful as pure logic, but it's as clean. So it makes it really a lot harder to make things like confusing kind of mutation dependencies, and your code is doing things you don't expect. Every function, if you call it with the same arguments, you always get the same thing, because there can't be some hidden data in there that's mutating or changing something you don't realize it's changing. It can't change something, and everything you pass in is going to determine what you get out. The problem with that paradigm is that it's not true. Computation at the lowest level, at the very basic idea of computation, all of it is just mutation. When you're mutating the values in processor registers or changing the values in memory, that's what computation is. A computer is just a big chunk of mutable state. So as useful as that pure functional paradigm is, oftentimes, it's just not true. And especially in environments where people are dealing with the bare metal. They're at the bottom of the software infrastructure, and their things have to perform really well, or they're just literally right at the level where they're actually literally having to mutate things like memory mapped, GPIO pins, things like that. Then this paradigm is just a non-starter. It doesn't even make sense. It offers no advantages at all. In a way, the Rust community is a perfect place to point this out. Rust has mutability baked into the type system, and things are mutable by default, but mutability is a very important part of Rust because it has to be practical. So the tricky part is that something like Coq, right, these proof languages we were talking about, it actually kind of does make sense for those to be pure and functional, because they literally are just representing logic. They literally are just it's type theory, basically. You take type theory, which is a branch of logic, and that you can use to define mathematics. That's all these languages are. They're just a type theory as a programming language. So we still want to be able to kind of make rigorous logical assumptions about our programs, but they also have to be programs that are realistic, that mutate state, that are doing the things that computers actually do. And that's what separation logic is going to come in. This is the last idea I'm going to talk about. It's a framework for doing this. But before it really makes sense to talk about why separation logic is cool and how it relates to Rust, incidentally, we have to understand what it's reacting to first, which normal logic. So this, P and Q is what this is. That little wedge in between P and Q is AND. It's the AND operator in formal logic. And P and Q can be any assertions. It could be I have 3 cookies and it is raining. And if both of those things are true, then P and Q is true. And in normal logic, it's perfectly equivalent to take P and Q and transform it into P and Q and P. You can kind of take the P and copy it. You can just duplicate it freely. Because, if I have 3 cookies and it's raining and I have 3 cookies, that's logically equivalent to just the original. I haven't changed the content of this statement at all. And when we're talking about things that really are kind of pure logical facts, things that are true forever, that makes sense. That's fine, yeah, because 4 is even, and 1 plus 1 equals 2, and 4 is even. That's not very useful. Maybe it's not something you'd want to do, but it makes sense. It's logically consistent. But when we're working in a system maybe where we're trying to verify a program, and one of the assertions we're going to have about some maybe point in our program, right here in my program, maybe one of the assertions I could have that, location or memory location A points to 1. That's what this might. We could choose to encode that idea with this syntax. So that could be a logical assertion. That could be one of those P, P or Q, that says, we know this points to this. And that's something that can change in a single instruction in a real computer. That's something that's not true forever. It's true right now at a particular point. So these comments are kind of showing a syntax that formal verifications often uses to describe, here's the state of the program at this point. And so, we might have at this point, okay, we know that memory location A points to 1, cool. And, maybe this is Rust and we can dereference that A and we didn't change it, so it's still true. And we can assert this, and maybe this assert is a function that will crash the program if this thing isn't true. And it's still true. So this all makes sense. This is all perfectly consistent. But, if we do something, that could possibly invalidate that statement, or that could make a new statement on top of it, or that could do some, whatever, such as calling a function. And we don't even have to necessarily give this function A. We could just call a function that does something. We don't know what it does. Then it might create a new assertion. It might try to duplicate this knowledge. Well, maybe it leaves us knowledge, but it tries to duplicate it in the sense of normal logic. And all of a sudden, it's possible for our program to be in an inconsistent state, right? A state that just doesn't make any sense. If memory location A points to 1 and it points to 2, and that doesn't make any sense. And the thing is, the rules of normal logic, if you're going to use ands in your assertions about your program, they don't stop you early enough from doing that. It's really easy to make that happen. And this is what was happening in formal verification before separation logic was invented. Separation logic was invented in something like 2001. Is that basically if you had a little piece of your program and you could reason about its correctness, if you wanted to put it together with other things, it got way harder because you said, oh, well, you know, I have all these assumptions I've made, and how do I know that no one else is making contradictory assumptions, or I don't know what's going on. That's where separation logic comes in. So this statement is pronounced, we have A points to 1, and then separation logic, instead of the little wedge and, uses this star, and it's pronounced and separately. It's called the separating conjunction. So, and points to, or, A points to 1 and separately A points to 1. And in separation logic, even though these two statements are consistent with one another, this isn't allowed because they're both reasoning about the same piece of state. Because the rule of this separating conjunction is that anything you put together with it has to be disjoint. They have to be talking about separate pieces of state, which is why it's called separation logic. So, this is okay, as long as, A and B are different. You can have different assertions about different things, but the point is that they've, with this kind of logical system baked into it, in the rules at the bottom, are that you cannot take something like A points to 1 and just duplicate it, right? Because that would just be inconsistent. It's not allowed. Or it could possibly create situations where you've introduced a real inconsistency. So, probably all the rustaceans in the room are kind of seeing maybe a little bit where this is going. Of if I have some knowledge at some point in my program of A points to 1, and I want to let someone else in on that knowledge, I can't just copy it for them. I can't just duplicate it for them. I have to give it away. I have to give them ownership of it, which means I don't have it anymore, which means they can change it, they can mess with it, it's theirs now, and I don't get it anymore. And I can't, the rest of my program can't make any assumptions about A. It has no idea what's in A. And so it's not a coincidence that Rust kind of has this idea because separation logic directly inspired a lot of the researchers and the people that made Rust. It's the thing that makes the Rust ownership system what it is. It's the straight line between the two. So yeah, that's cool. So, so this idea of separation logic has already given us something really powerful, which is the Rust borrow checker, the Rust ownership system. And, the example I'm giving there is it's probably obvious to you guys that it's a little too strict. I can't give away any knowledge. I can't share any knowledge. Rust is more complicated than that. You can have multiple read-only copies of something and only one mutable copy and all this kind of stuff. So technically what's going on is that the borrow checker is like a proof checker. I guess it's not really a proof checker. It is a proof constructor. It can figure out a proof. Not really. I guess it's not actually what it's doing. Whatever. I'm not going to get hung up on that. But basically what it is it's a proof checker for what's called a decidable subset of a fractional separation logic. Again, whatever. I'm not explaining all of this, but that's technically what's going on. But I say decidable subset because, it's probably not possible to write an algorithm that could always just look at a Rust program and figure out that even things that use unsafe are correct. We can't build an algorithm that can just always figure out for us if everything we're doing is consistent. And that's why this is a decidable subset. There, for the Rust borrow checker, this algorithm can always, if it's all safe Rust, go across our program and just figure it out. Yes, all this is consistent, everything makes sense. And I can guarantee that all of this is reasonable and your memory accesses are correct and all your data is going to live properly and you're not mutating things or whatever. But, if you only could do safe Rust, we wouldn't be able to do anything because that's not strong enough to be able to write all the programs we have to write. We need unsafe. Unsafe is underneath everything in Rust because it has to be. Otherwise, we couldn't implement basically all of it at the bottom because the borrow checker can't figure out that everything else is correct. Not when it's too complicated. Not when it uses unsafe. And it's probably logically impossible. That's what this comes in. So there's a project that's fairly recent. I think some of the final papers came out, or the papers came out in like 2018, called the iris separation logic. And basically, it was built by a team of academics. And the idea was that they were trying to verify arbitrarily complex Rust programs. It's written in Coq, kind of that language I was talking about before. And here's some papers. These are a lot more punishing. Jumping into these directly would be very, very difficult. But the cool thing is they were able to basically model the Rust type system and on the ownership and lifetimes and send to sync and everything. And they proved in Coq that the Rust type system makes sense, that it's consistent, that this separation logic all makes sense. And iris is much more complicated than the borrow checker, right? It can prove whatever, which it was even also used to not only just verify the type system, kind of the algorithm that checks. I don't think they checked the algorithm, but the type system is consistent. But they also checked a bunch of these important low-level libraries, ones that are concurrent, ones that use unsafe internally, that have really, really complicated correctness conditions. And they were, again, able to prove that the algorithms being used are consistent, it makes sense, and are correct. And even there was some follow-on work. Someone made something called the iron resource obligation management logic that can even verify that all the resource stuff makes sense. So things like the program collects all the memory that it allocates and it doesn't memory leak, or that it handles all of the file handles that it opens, or things like that, just kind of resource obligations. I mean, that's really amazing. That's this thing of, this tool that people are using, and all of the things that people were scared about that underpin it. This system is powerful enough because these researchers are writing, actual proofs, manual proofs, rather than just having an algorithm figure everything out. They're able to prove the correctness of all this stuff. It's amazing. Okay, this stuff came out in 2018. Why hasn't this already changed the world? It helped the Rust implementation, but why isn't everyone doing this? I mean, the first thing is, again, research debt. Those papers that I was just pointing to, they're good. They're actually written a lot better than most academic papers, but they're still very academic. They have a lot of really weird, arbitrary notation. They don't tell you how to kind of parse through or how to pronounce. They use Greek letters at will. They have a lot of jargon that you have to kind of find for yourself, and they make it very difficult to chase down all the concepts you need to understand first. Yeah, exactly. But the real problem, the real reason that iris is not just already a thing that's changing the world, is that it's not actually a directly usable language. Things like this, it's a Coq library. It's sitting in Coq, and it's only built for on-the-side proofs. So they won't verify the actual Rust source code that makes up these things. That would actually be really hard. They translate it, basically, to kind of a Coq notation version of it. So this is is an example from one of those papers. This is the option as mutable function in Rust. And, that's not Rust. And they have a lot of kind of type theoretical ideas and whatever. They translate it into a form that was easy for them in the papers to reason about. And then in Coqland was easy for them to handle. And it's, they probably still got all this right, and I think their work is still amazing. But this can't just be picked up and used. We can't use iris to build things. So,
and it's not a formal verification of Rust either.
Yeah, not in the strict sense, because it's not applying to the actual literal implementation. It's just kind of modeling all these things from afar. Yeah, exactly. So, I mean, they did catch kind of some algorithmic bugs, for example, and they did back ports. They said, oh, this doesn't make sense in the implementation. We translated it, and we couldn't find proofs, and we did it this way, and then we could find proofs. And so that should be changed. And so they were communicating with the Rust internal teams and stuff. But yeah, it's not the implementation of Rust. It's probably even drifted, frankly, from what they originally verified. That was years ago now. So yeah, this is the dream of the Magmide project. And honestly, I'm probably way out of my depth with this project, but I don't see anyone else doing it, so I kind of said, okay, I'm raising my hand, and I'm going to start working on this.
So this is your project you're talking about?
Yes.
Okay.
And it's very, very early. So basically, the hope of Magmide is to take all of this amazing, right? These things of, just kind of software people tend to assume, oh, well, everything's broken, and you can't do any better than that. It's trade-offs, and you can't do any. No, we can't get all the way. We have to be humble still. Yes, there's always caveats to everything, but these kind of formal proof systems go so much farther than we ever comprehended as possible. And so the fact that no one even knows this exists, to me, is shameful, right? And honestly, it's shameful to these academics and to the culture of academia. I think that's a massive waste of human potential. But, that's a bigger problem than me. I can maybe solve this little problem. So, anyway, okay. So basically, my kind of theory about what a tool has to be to achieve the goal of taking this power and giving it to everyone, what it has to do with the kind of design constraints it has to follow are these ones. So the first is that it should make it possible to fully verify any piece of code, which basically means a lot of systems, Rust is an example where they say, okay, we'll give you this decidable subset where we can always just unleash an algorithm on it, and then you don't have to do anything. You write your code, and we can tell you at the end if it is wrong or something's broken that you need to go fix. But those decidable subsets, that's not everything. Again, it's impossible to write an algorithm that can figure out a proof of any proposition in the universe. That's like literally the P equals NP problem, right? Or one of them. I actually don't know if exactly that is true. But anyway, we have a lot more raw logical power than we're oftentimes giving to engineers. We're saying, cram your problem into here, and then maybe we can figure it out. And, I think that's dumb. The ideas of formal verification, I just kind of went through some of them, the most important ones, at least the ones that matter for real software verification. They're not unlearnable. Engineers learn really complicated, crazy stuff all the time. But engineers have time constraints, and they have deadlines, and they have resource constraints. So academics, it's their full-time job to be an academic and go read papers and produce papers, and not to build anything necessarily, right? Not to create something that can actually run or work in under duress. So they have the time to just deal with this research debt and wade through all of it, and we don't. So, I'm saying that engineers can understand these things. I think it's absolutely possible. It just has to be explained to them in ways that aren't laughably terrible. And then they have to be actually given a tool that gives them that power and that actually promises to help them achieve something with it. Not just, ooh, I have a little proof of Fermat's theorem on my computer, and how lovely is that for me? No, building something, creating something. So if you give people full logical power, you can always still have these decidable fragments inside. You can still write algorithms that make little parts of what we're doing. You can automate that. You can still have safe Rust, but then people should be able to verify unsafe Rust or whatever. Then the next thing is that, a system like this needs to be able to compile or basically to produce code, reason about and produce code for any environment or architecture. And the first way we can do that is just kind of piggybacking off the LLVM concept. LLVM is an abstract assembly language. It's what Rust compiles to, and it's the reason why you can compile Rust to basically any architecture without having to do anything. And we have to kind of do the same thing here. And the really cool thing about a logical system is that if you have some crazy, maybe you have like a particular chip that no one's ever written anything for, you can define how it works in a logical system, and then you can write code for it, and then you can prove that everything makes sense. You can use this system to talk about any new environment. Then it's really, really important that this thing is realistic and that it, just like Rust has, that it is incrementally adoptable. I mean, Rust has unsafe for a reason, partially just so that it can do all the things it wants to do, but then also so that it can interop with C, so that instead of having to replace a huge legacy system, maybe in C or whatever, all in one big chunk, you can kind of, oxidize it. You can slowly eat it away with little sub things. And something like this has to do the same thing. One of the key ideas that we can kind of use to make this even more practical is something I'm calling trackable effects. And I'm not going to, we can talk about this more if you guys want to, but basically we'd really like to be able to write code that is actually broken and that maybe isn't even safe or it has all these possible negative problems and still be able to run it. But we'd also like to know that it isn't safe. So, in Rust, you can have unsafe stuff happening, and then you can wrap the unsafeness and hide it from people, even if what you're doing is not correct, even if it's not safe. So essentially the idea of trackable effects, it uses kind of the iron stuff I was talking about, one of the Iris projects, is that, if you're going along and you do something that is possibly dangerous and that could jeopardize a thing like memory safety, or it could make it so your program runs forever or whatever, and you don't justify the safety of that operation with a proof, then basically your program gets infected, or this function gets infected with this trackable effect. That basically says this function is not known to be, it is not proven to be memory safe. And you can run it still. It's still a function, but we know that. And if someone else tries to use it, they can still use it, but they'll know that. That effect will follow that everywhere it goes. And since we have a proof system, it's actually possible to do whatever you want, but then say, no, this all makes sense, and here's a proof. And then I'll say, okay, cool, everything's good. And then we want to basically make all of this labor really reusable. Because it's obvious that, not everyone is going to write really granular proofs of all the stuff they're doing all the time. That's not realistic. But we kind of would like to have what I'm calling the verification pyramid, where at the bottom, some people do have to do that kind of work. If you're writing an operating system or a kernel driver or a network protocol router, now I'm trying to think for it, a network driver, there it is, or a cryptographic library, that has to be right. You know what I mean? It's like really got to be right, and you have to do an amazing job of writing all the proofs and figuring out how it's right. But then if it's possible to kind of pass on what you've done to higher levels, making it so that you can, maybe in an operating system, if you can create a provably secure set of abstractions that the user land of the operating system can use. Or if you can use Magmide to build programming languages, and maybe using metaprogramming, you can say, okay, well, you can define a language, you can build a language compiler in Magmide, and then at this level, people can do, they can have a nice algorithm that just type checks things for them, so maybe like Rust, safe Rust. And everything up here can be pretty easy to reason about. No one has to write proofs. But if we let them have an escape hatch back down into this full system where they can write proofs to say, oh, I want to break out of the rules of this higher level language that most of the time everything's easy and I just write code. But occasionally I want to drop back down and do something more advanced. Then having that power available, you don't have to use it all the time, but if it's available, that's better. So anyway, verification pyramid, excruciatingly verify things on the bottom, and going up, passing all of that, giving that a foundation for things that matter less. A recipe app doesn't have to be all that verified, whatever. It'd be nice if it was memory safe and secure and wasn't going to get your machine pwned. And the lower levels can give it that. They can pass on those kind of guarantees as long as everything's reusable. Okay, last points. And then, it shouldn't suck to use. Rust has taught us that we can have nice things, even when we're really solving very difficult, very low-level problems. We can have good tooling. We can have nice things. And then, I've been hitting at this all through. These ideas are not unlearnable. Some of them are kind of complicated, a little bit. One or two of them has, a conceptual leap you have to make. But, again, engineers learn complicated things all the time, whatever. But these things just have to be taught in ways that actually respect people's time and that are trying to teach them. actually, and not just writing a paper for academic reasons. So, I don't know. I mean, I kind of envision a world where things aren't all broken all the time. And at the very least where things are secure, at least most of the time. So I guess one more slide. Just about, how do you actually build a language that achieves that goal, all those design constraints. And I guess this is the core idea, because like I kind of hinted at, a proof language actually makes sense to be pure and mathematical and not practical, so to speak. But you need a real bare metal kind of computational language to go along with it. So that's the core idea, is Magmide is separating the two things. Where logic Magmide is like code, honestly, maybe better designed, less whatever. But it's kind of imaginary. It exists at compile time. All that it is used for is to reason about the real computational language and to constrain its behavior. And then this host Magmide because it's actually running on your machine. It bootstraps. The two kind of things are in this self-reinforcing loop. So yeah, it implements itself and it implements logic Magmide. Yeah, and I guess that's the goal, is that in the exact same way that we're slowly moving towards Rust instead of C, because, it just gives us much more ability to write things that aren't broken, aren't going to cause all kinds of problems. Magmide wants to be to Coq and LLVM what Rust has been to C. That's kind of the goal.
So what you're saying is you want Magmide to be both the low-level compiler that can emit assembly to all the different platforms,
yeah,
and the intermediate representation, and a formal logic system that will help you prove it all works like you think it does.
Yeah, I mean, I guess, yeah, okay, so, okay. This, I'm great, I'm glad you asked me this question. So, you know what? Let me just finish, and then we'll kind of go into those, like, deeper. So there's the repo, and thank you. I guess I just had to, like, finish my slides. So there's an academic project called Coq Correct, and they're making the rooster joke. And basically what they did is they, in Coq, modeled the semantics of Coq and proved that they were correct. So I mean, like, it's impossible to prove that, like, you can't use Coq to prove that the type system of Coq is correct. Like, it's Gödel's uncertainty theorem, right? You can't use a logic. Never mind. You can't use a logic to prove that it is itself consistent.
Right, but you can't escape a logic system or something like that, right?
Yeah, but you can use a logic system to prove that the implementation of the Coq proof checker is correct, right? Because then all you're doing is you're kind of saying the rules of the Coq language, the type system or the proof checking, whatever, those are called axioms. And that's something I'm getting at here. Your question was about, well, you still have to bake your assumptions into the AST you create. That's true. And that's kind of the place where we have to be humble. Well, that's part of the reason why Magmide is going all the way down to the bottom. But yeah, you have to define your axioms, your assumptions, and then you use those to prove things are consistent. The reason that still works is that, if you're working in a typed language, for example, and you get your types wrong, I said that I have a string here, and I really meant to have a Boolean here. Later on, when you try to use that to do something that you're expecting it to be able to do later on, it's going to get mad at you. And you're going to say, there's an inconsistency because I made a mistake here. You won't always catch those. Sometimes it will be like, I made a mistake, and that's a really big problem, and it causes things down the line. But it's the same kind of thing with these kind of proof systems. If you have your axioms, your assumptions of your system, and if they don't make sense, if they actually aren't consistent with one another, then when you're down here trying to prove things with them, you're trying to use them to prove some higher ideas, you'll find that you won't be able to, right? Things won't line up. It won't make sense. And so you'll have to say, wait, did I do something wrong up here? You know what I mean? And that's kind of why also this language is saying it wants to step in the same role of LLVM. Because it's basically, in computation, even something like an operating system is just a piece of software. So to say that the operating system forms like a foundation for other things, that's true, but it's software. So theoretically we can prove that it's correct. theoretically. The only place where we have to go all the way down and where we can say, oh, well, we can't be sure below this that we're right, is the hardware, right? We kind of assume the hardware it does what we say we think it does. We kind of have what I'm calling hardware axioms. We just state these things like, if these aren't true, then we're screwed and whatever. But, hardware does a decent job of being correct most of the time. There's layers of error correction and stuff. And that's the kind of layer of humility we have to have of, yes, machines will break, cosmic rays will happen, stuff like that will happen. But if our hardware axioms even try their best to kind of introduce the idea of possible corruption, and those kinds of problems that make it so even the hardware can be unreliable, then we can even try to contain that a little bit. But yeah, that's the lowest that we can make kind of assertions about. And we can state the hardware is that axiom. And then, again, this is a million miles away, but if Magmide achieves the goal that I'm trying to have it achieve, LVM, I'm just going to find this picture. It's such a good picture. Where is it? Yeah. So, the way LVM works is that you have all these different languages that output, they output LVM, and then, internally LVM does stuff. But then they basically have a bunch of backends for LVM, where LVM can be compiled to all these different actual chipsets and environments. And the reason Magmide wants to be at that level is because that is kind of, LVM makes sense. It's a good way to do this. And if there's a proof language right alongside this thing, then basically all of these backends, we can do that what I'm talking about. We can define the hardware axioms, the literal assembly language instruction set of all these different infrastructure or architectures. And then we can have proofs, right? We can verify the translation from our Magmide intermediate representation or whatever down to the real thing. So the point is that, with a proof system in hand, we can get all of this, all the way up and down, all the way down to the metal, that it's all correct. So basically there's a bootstrapping process that happens here. That's kind of what I'm working on right now, is that first you have to use something like Coke. That's the first step of this project, is to use Coke to kind of, basically what I'm going to do is I'm going to translate Magmide's syntax using Rust, parse it. Coke is written in OCaml, so you can kind of bridge, your values across into OCaml and get them into Coke. And you can do proofs on them. You make sure everything makes sense. So then you can define the semantics of host Magmide in Coke. And then prove that you write functions in this, and then you can use just existing Rust LVM stuff to Inkwell is a LVM binding library that I think is good. And then you can take your Rust code, your abstract syntax tree, and then compile it to LVM. So the point then is that, there's a lot of steps there, and it's still messy, but it's kind of the bootstrapping way of saying, okay, we have a thing, we've proven stuff about it. We can say that these, LVM-like programs are correct according to whatever. And then we have an LVM object that we can link with other stuff. We can link it with other Rust code, and we can slowly begin this process of bootstrapping this whole thing to the point where, because at the end, we just end up with assembly language, right? But it's assembly language that we have proven stuff about, that it implements the proof checker correctly, that it, parses things correctly, that it does all these things, and slowly get to the point where the system is built in itself, where it's all defined in itself. Now I'm actually done. Cool.
Okay, so if we say, it succeeded, and it's 20 years in the future, then where is Magmide? Let's say I'm still writing Rust. Where's Magmide?
I think it sits in the spot that LVM sits in, right?
Okay.
But so basically that's the more idea is it's LVM plus a proof language.
Okay.
Right? So that right at the lowest level, when we're kind of going the last mile, we can also reason at the lowest level. Right?
Okay.
We can prove
sort of like Rust is okay, we need a tool that we're using C for right now, but it just has all these sharp edges because it doesn't have this paradigm of rules that keeps it safe.
Yeah.
And I'd say, well, okay, LLVM's like that now. It's sort of like C, where they made it up. They had to get something working. It was a great idea, but it doesn't have like a paradigm of rules to keep it safe. So what we're going to do is introduce a whole new proof checking, type checking system in an LLVM-like project.
Yeah, right alongside of it. Yeah.
Displace LLVM like Rust, in a sense, displaces C.
Exactly.
With a nicer thing to use.
Exactly, and something that's more powerful, right? Yeah, because Rust is more powerful than C.
Right.
It can reason about more stuff because of the borrow checker. And the same thing with this, yeah.
So once you've got a Magmide, does that mean that you also have to notate or add some code to the Rust code to get it to work correctly, or does Magmide just automatically do the checking?
Well, yeah, so I guess it would depend. So that is one of the goals, possibly, of the project, is for it to be used to make the new implementation of Rust, right? To kind of do the Rust compiler again, but have it all verified, like actually verified. So it kind of depends. So again, like I'm talking about, there's these decidable subsets. Decidable means that you can have an algorithm that can always just run and tell you yes or no. And it's not uncertain. It's not no as in I'm not sure. It's yes, this is safe, or no, this is unsafe for this reason. And so a lot of time, yeah, we still can do that, where you can kind of write in this close subset. You can write safe Rust, and then you're just good. You know, maybe you want to do extra stuff. I mean, here's an example of.
Okay, so what
Sorry, maybe I'm talking too fast.
Express right here is that if this all succeeded, then Rust using Magmide would enable things like unsafe Rust
To be
no longer
proven
be
safe.
Unsafe.
Exactly, yeah.
You do the things you do with unsafe, but now it's safe.
Exactly.
Because Magmide enables checks
Yeah.
that couldn't be done with LLVM.
Yeah, exactly. So if you can keep it within one of these decidable subsets, you can keep it in safe Rust, you don't have to write any proofs. You're just like, okay, it's safe. Maybe you want to prove that it's correct higher, right? Why don't you say, oh, my parser isn't just memory safe. It is correct. It does the parsing thing that I want it to do. And then you start writing proofs on top of that. But that's the whole thing, is that you can just have code that works, and you start layering on top of it proofs and assertions and stuff. Kind of like the even example we gave back here. Oh, golly, where is it? Let me find it.
So,
Ooh.
like, in terms of ergonomics, do you envision the way we write unit tests today is replaced, or
Maybe
we
somewhat.
improve it with, we would have proofs for critical portions of the
For
code,
critical.
or-
So I guess it's kind of like this verification pyramid, where probably you start with it type checks. And it type checks maybe is it safe. And then you maybe move on to just some sanity checking unit tests, and you just do the normal thing. But then maybe we have a next layer of, have you ever heard of quick check? People heard of quick check? Things like quick check, it's a Haskell library. Rust has a version of it. But basically a quick checking thing is you just kind of, let me just find it. I can just show you stuff. Let's just show you stuff. Yeah, here's the Rust version of it. So basically, you have a test. Here's this prop. It's basically a test. And, because Rust is cool, it can say, oh, you're giving in a vector of unsigned 32 integers, or U32s. Then I'll randomly generate a bunch of vectors of U32s. And then I'll just run this check of yours over and over and over again to make sure that it makes sense. Right? So that's cool. It's a kind of a better way of doing unit testing. Instead of coming up with specific examples, you're instead saying, hey, use the type system, generate a bunch of random examples, and try to find one that is incorrect, that fails this test.
So it's fuzzing?
It's basically fuzzing, yeah, but it's more kind of direct fuzzing, right? It's not like literal binary fuzz. It's types, right? Or just kind of giving them to you, yeah. Or it's typed values, I guess is what I mean to say. So the thing is, you can do that with this kind of proof stuff too. So this is kind of one of these proofs that you see, like double, its type is really simple. Right? It doesn't have like that one example we gave where the type is really big and complicated and asserts the behavior of the type, or the function in the type. This even double is a proof that's on the side. It talks about double, and it proves something about double, but double doesn't have to know about that or be changed. So yeah, this is like a unit test, but it's infinitely better. But with something like a quick check system, we could basically have a quick check, basically just look at this thing and say, oh, I haven't proven this yet. I don't know how to prove this. I'm not sure if this is true. This might be true, I'm not sure. And you can have a quick check kind of just say, hey, generate a bunch of things and test them if this property is true. And if you find a counterexample, you say, okay, cool, I'm not going to try to prove that because it's obviously wrong. Here's a counterexample. But then maybe once we get to that level, you say, okay, maybe that's good enough. Maybe you just stop there. Because not all software has to be critically correct. But if it's really important, and you say, okay, now we really like to know this is right. Or maybe we want to use the fact this is right. We want to reuse a proof of this being right to prove that something else is right. Because that's the way that you can kind of use these functions. Again, these are proof functions, so you can reuse them in other proofs. And so maybe you say, okay, well, let's tackle proving it. And when actually using Coke, this is probably the one good thing about it, is that they kind of have an interactive system where I just, we're talking about stuff. Let's just do it. What is this? That's something else. If you guys just want to listen to me talk forever. Oh, golly. That's turning out to be really slow right now. Okay, where is this? Let's just grab some of this stuff. So, here's some stuff, some things that I've proven, and, here's my talk. I'll just go from the talk directly. There's one cool, here's a even definition. Oh. And then, there it is, even double. So the way you actually use Coke as you're doing things, no, that's fine. This is a little fidgety. That'll work in a second. There we go. Okay, is that you kind of have this interactive, what do they call this thing? I guess it's just the interactive, Coke, the Coke whatever. But I kind of go through, and I go through my definitions one at a time. It says, okay, cool. And then I can go through one of my proofs. And what it basically does is it shows to you, okay, here's the thing you're trying to prove. Yeah, that's kind of hard to see, isn't it? Let's make it a little bigger. Ooh. So, over here I say, here's my goal of the thing I'm trying to prove. I'm trying to prove that for all n, doubling n is even. And then maybe I'll go, let's try doing an induction over n. Just like I actually do it. It says, okay, now you have two goals, and I can focus down on the two goals individually and say, okay, all right, so even double is 0. Interesting. Okay, well, let's see. So this is kind of the thing. If you're in kind of a REPL, right, where you can kind of play with this and try stuff and kind of go through and slowly figure out your proof. And that, honestly, this is probably one of the best things about Coke. It's that this system's pretty robust. Or, this particular thing in Sublime Text sucks and it crashes all the time. But, let's see, how does this work? I can't remember what the, hold on. Now I'm trying to sit here and figure out how this actually worked in practice. Is this an assumption? Can I just call? No? Let's just try this again.
Something I'm curious about.
Anyway, never mind, sorry.
Talking about the dream of Magmide and what it would be. There are some things that, like if you have it at the LLVM layer, I don't personally as a programmer deal with LLVM.
Exactly.
Really ever. So, like my experience, if it was just at that level, it wouldn't change as a developer. But the hope is that this would almost show itself into what I'm doing as well, right? That I can write, like in Rust currently, I can't encode that type of easy. That's not really, not in the type system certainly.
You can a little bit with const types now. Anyway, it's more, whatever.
But not certainly as robust as this. Is that, I don't see a way to escape adding something, some kind of syntax or something to Rust.
Yeah.
To be able to
Yeah.
encode some of these more verifiable assertions, right? So is that the idea too? Like you would have to integrate with the language to some degree to be able to say, well, currently being able to check these things is not the same cut as verifiable as Coke is. So
Yeah.
That's part of it as well, is to integrate with languages.
Yeah, well, so the way this would probably happen is, let's say, a language like Rust is implemented in Magmide. And let's say Magmide has really good metaprogramming stuff. So, I guess the real idea that we're trying to drive at is that maybe Rust can have a new top-level keyword. It can have I don't know, I mean, proof. It can add some syntax to the language. That basically all it's doing is just dropping, it allows you to define maybe logic Magmide, in a way that makes sense for Rust, but in Rust. So yes, you do have to kind of lift the logical part up into higher level languages, or at least give people an escape hatch to just write logic Magmide inside,
so that it can be bootstrapped. Because that's like, when you're kind of saying like, okay, we have unit tests, why don't more people use this? The biggest thing to me is development is so iterative. Mm-hmm. It's very easy for certain checks or documentation, anything that essentially isn't checked for correctness
automatically,
it basically becomes, within a very short amount of time, very stale.
Exactly.
So I assume that happens with proofs and code a lot.
That's interesting, because I mean these tactics that I'm doing, these tactics, right? They're kind of functions that are they're metaprogramming. They're looking around at your goal, the thing you're trying to prove, and they're trying to come up with, basically code that does it, that proves it. And so sometimes, you'll change your thing slightly, and you can have a tactic that usually is able to, even you can change it a little bit, and your tactic can still find the answer. But maybe you change it, and so now it's broken. But it's broken in a way that won't type check anymore, right? It'll fail. So you'll at least always know that. I kind of see what you're driving at, is that we want to take this level of safety. It's perfect if, right? It's beautiful. It's a great experience if we can lift it into languages where it's right there, and it's in the same type checking loop as people are already working with.
It's integrated, right?
It's integrated.
It's a big problem. Right?
Yeah, absolutely.
That's kind of like what Rust did with documentation. That's just really nice, is that it's so integrated that it's far easier as you're developing iteratively to keep that in check, right? Your examples, they're compiled, they're tested against what code you have, so it's very tied.
But where is it integrated is the critical point there. Like where is the documentation language integration barrier running?
Are you talking about? I guess because
I'm talking about his point about the documentation experience.
But it's like in the compiler.
So the point I'm driving at is these proof systems can only happen either at compile time or in LLVM's case, like between compile to the intermediate language and like the assessment internals of LLVM before it gets to machine language, which is just another compile set, really.
Yeah.
So
you can write functions that maybe.
Yeah.
I mean, you can prove that a proof checker is correct, and then you have a program that runs at runtime that. Anyway, never mind.
It's very meta.
Yeah.
But so it's not something that like your editor can do, unless it's running the compiler.
It has to be running in a loop with something. Yeah.
Is exactly what the language server for Rust is doing in various editors and things like that. But that was my point about you're noting the documentation integration, and that's part of the compiler. And so the Rust compiler has to be involved, or the LLVM middle compiler from front end to back end has to be involved.
Yeah.
And in order to do this proof, it's in the workflow that you're talking about, and what you seem to be alluding towards this.
Oh yeah, because I guess
it will be in the compile step as like a language extension.
Exactly.
Or it's an LLVM step that you have to pass notation from your Rust code to the LLVM notation so that the proofs can run against it.
Yeah, or even like, I mean, okay, so if you have like the Magmide compiler, right, then especially if it's a well-designed compiler, if it's like a query-based compiler, for example, where it's really easy to take little individual things it does and reuse them in other places, then, if the Rust compiler is written in some variant of Magmide, then it can just use the Magmide proof checker, right? It can just like call the Magmide proof checker in the Rust compiler.
Yeah.
You know what I mean? It's integrated because you can just reuse code from here when you're implementing a compiler up here.
Are you saying that Magmide is
not could be. It's basically nothing right now.
In this theoretical future set, not just an IR that the Rust code will compile to, but also a higher level language itself that the compiler would need to be written in? Because that's how it sounds when you're saying.
Well, no, I mean, I guess it's both of those things. I don't know. I mean, it's everything at the end of the day, because now we're just kind of like talking about metaprogramming and the that is metaprogramming. You know, it's Magmide would just be a compiler, right? It's a compiler. And the internal data structures that it uses to represent the concepts that eventually implement it, right? The data structures it uses can be passed to it from anything. And the functions that it uses to check things are correct and whatever can be called by other things. So yeah, I mean, you just have the Magmide compiler functions and data types. And they can be reused in other projects in ways that make sense with those projects. And so maybe you have Rust, you know, maybe Rust has its own IR, it has its own intermediate representation, but maybe they, you know, are able to write a Magmide function, and they prove that Magmide function can always take Rust IR, and if that type checks, then that follows some sort of set of propositions that are defined in Magmide. You know what I mean? It's like, it's the meta-ness of it, we can sit and kind of chase our tails forever.
So it could be any.
Yeah, exactly.
It could stay how it is now, or the Rust front end emits Magmide IR.
Or just, yeah, people would just make kind of architectural decisions. But what's easier? I don't know. And one of those books that I talked about is the Certified Programming with Dependent Types. He calls the idea of writing a function that you then prove, you know, you prove that function, if it returns a certain thing, proves something about its input. You know, if this function says yes on this input, something's true about that input. And basically what he calls that a certified decision procedure, you know, and you can use those in proofs of, hey, at compile time, just run this function that I've proved does a thing. And then if that function says yes, the proof's over, you know, but I did that at compile time. The construction of the proof is running this function. You know what I mean? It's like, again, the meta-ness of it.
Well, I really like how you said that the sort of the Rust brought some of the proof into the compiling, because it really did. I can look at a function signature and say, okay, I know this function doesn't change anything, because the type system won't let me change anything.
The type system
right?
guarantees it.
I'm only using an immutable reference as an argument to this function, therefore it will not change the data that it's pointing to. It is the proof, because it's the type system.
Writing the code is the proof. Yeah, exactly. If the code successfully type checks as a thing, then the existence of that code is a proof that that thing is possible. You know, yeah, if I write a function that that has the type of transforming a number into a string, then I've proven that that can be done. That's like dumb, because that's easy. I can just, you know, give it a string that has no relationship to the original thing or whatever. But yeah, the existence of code is a proof if it type checks.
So I like the idea of pushing that down into the LLVM layer and enabling not only new features at the LLVM layer, but that then in turn enables features up in the higher languages.
Yeah. So one of the really cool ideas that some of the papers and stuff in this world talk about are things called proof-carrying code. So the idea of having assembly language, but maybe like in its data or string section, has kind of, you know, data that represents proof stuff about this assembly language being correct.
That's sort of like debug symbols now.
Exactly. But like proof stuff, right?
Proof symbols.
So the idea that being then that, oh, you know, with a system like this, if you have the Magmide compiler, then you can put the Magmide compiler in something like a web browser. And you can just scrape code from the internet. And then if that code provides proofs of, no, I'm well behaved. I'm only going to touch this. I don't look at memory. I'm memory safe. I don't do any of this, right? I'm going to be nice. Then you can actually statically say, oh yeah, this could have come from North Korea, but it type checks. It's safe to run in ring 0. You know what I mean? We can give this thing, we can run this thing unsandboxed, and we can verify just by running a type checking algorithm over it that it's safe. Maybe we still wouldn't choose to do that, right? But even then, we could prove that our sandboxes are secure. You know what I mean? It's especially at the lower levels. This is a lot more tractable because what it means for a program to be memory safe or to always terminate, you can prove that certain programs terminate always, but they'll never run away forever. Or that, I'm trying to think of other safety conditions. I mean, you can even write, the idea of trackable effects so far is to make the trackable effects system kind of open and generic, so that you can even have things like, oh, we can have an effect representing the idea that this web server never leaks secrets, or that it never renders raw, untrusted user input, or that it never, you know, executes foreign code or whatever. yeah. So where was I going with that? It's just it's especially at the lower levels of the stack, the things we could possibly do are a lot more amazing. Whereas saying, oh, my recipe app is correct, maybe even the definition of correct is a lot more hazy. But again, the lower levels, the definition of correct is pretty well understood. And so it's more possible to start nailing that stuff down and getting absolute certainty that it's all right.
So you said this is really early. How really early? A bunch of markdown docs in a repository?
There's a lot more than that.
Yeah, we've got warnings all over it.
So I'm asking, what have you done so far?
What have I done so far?
And is it just you?
This is it is okay. I mean, I guess a kid from St. Petersburg reached out to me. I mean, that's the thing is more people have been interested than I expected, which I guess I shouldn't be super surprised.
Have you looked at there were 2 or 3 groups of people who were talking about Rust for critical programs for aerospace.
Ferris systems, yeah.
And yeah, the thing with Ferris systems and I don't know if that compiler that they're working on is meant to be open source or closed source.
I think some of that was recent, right? Because the Ferris systems was pairing with Ada Core. I mean, as I've been kind of working on this idea, I've been looking around at all the other projects and kind of saying, yeah, just do I think this will do it?
There were some other groups of people
Besides Ada Core?
Those 2 groups
okay.
talking about the need for that. I don't
okay.
know. They're the only ones that seem to have done anything so far.
Okay. I mean, what I've done so far is I've written a Coke plugin, the thing that kind of can take code. I mean, that's all it does at this point. I figured out how to make Coke kind of, ingest foreign source files and build Coke stuff from them. I've written a bunch of kind of exploratory proofs about especially proving termination, actually, of programs. In an assembly language paradigm, where the execution of an assembly language program is just the program counter changing, and pointing to a different instruction in memory that it's going to run. How do you prove that it's going to terminate? And I was able to find basically the conditions under which you can define the execution function or whatever, that you can say, oh yeah, this can be proven to terminate. I haven't proved a lot of interest or really any very interesting programs that they do terminate yet, because it has to do with something called the lexicographic ordering, and anyway, I'm not going to go into it. But I mean, not a lot, because part of the reason I haven't just charged ahead is that, I mean, I have a full-time job, and I have been burned a bunch of times by having an idea. I say, ooh, this is a cool idea. I should go with this. And I just chase after it, and I disappear for a few months. And then at some point realize, oh, actually, I mean, like as an example, I wrote something called macro-TS, which is basically, it's a wrapper around the TypeScript compiler that has macros. It has kind of type-safe macros, right, where you can do macro stuff and it'll expand and then it'll type check. And then at some point I said, oh, I got it working, right? I spent like 2 months, I think, last summer doing it. And then I said, oh, okay, well, no one's going to use this because it's not going to integrate with the language server and the error messages. It's just like, I just realized this is a harebrained idea. TypeScript should have this. This is obviously a good design for an idea. But Microsoft has to do it. I can't just hassle them. And I can't hack into their really specific thing. The real problem is underneath. I had this idea kind of, bubbling in my head at this point. I said, I just do the real thing. The thing that I really should be doing is something like this. Magmide. It wasn't called Magmide at that point. But I don't know. I guess I've been trying to get out there and say, hey, is this a good idea, world? And it would be nice to have someone say, yes, come here and do it. Maybe because I think if I've given 6 months, I could get it to kind of the useful proof of concept prototype phase, to the point where you can ingest code, you can get into Coke and prove stuff about it, and then you can output it. And especially the idea of trackable effects and integrating with Iris, because again they're very academic. That's probably going to be the hardest part of kind of doing all that theory and defining that system. But that's the interesting idea that's at the heart of this. It's that idea of effects is kind of different than all the existing literature about effects. And it's a thing that I think would make this practical in a way that's not, like a lot of things like Iris, for example. A lot of these systems you just have to do it. It has to be correct. And you can't write something that's broken and get to the proof of correctness later. And while you're iterating, that's part of it. You want something like, I don't know what I'm doing yet. I'm going to give me this and run it, and then I'll see if it does that thing that I wanted to do, and I'll get to proving that it's right later. Maybe or maybe I won't. Maybe I'll just whatever. But it seems like that's the thing that I have to really nail, and I'm doing it all in my free time, and I can already tell I can't do that for very long.
Why don't I ask one last final question, and then we'll finish the recording part, and then we'll still got a half-hour chat.
Oh wow, that took me a long time, didn't it?
Where did the name Magmide come from?
The name Magmide. There's pretty extensive documentation about this and the issues and stuff. So originally I wanted Bedrock because this is the bottom of the stack, right? It's a foundation for all verified software.
100 million Minecraft kids would probably.
Yeah, so that's a taken name. It's taken by, there's an MIT professor who wrote Certified Programming with Dependent Types, one of those books I referenced, that one of his MIT programming language, groups has a thing called Bedrock. It's smaller in scope. I don't know. It's academic, right? They haven't shipped anything necessarily, and there's a lot of papers that are cool, but whatever. So it's like, okay, I can't do Bedrock. That doesn't make sense. And then I wanted Magma. It's like, it's not Bedrock because it's abstract and it could be for any architecture,
okay.
so it's Magma. Right, Magma. But then there's a computer algebra system called Magma. And actually for a little while when I was first putting this on Reddit and stuff, I was saying, hey, am I stupid? Is this a good idea? And I was calling it Magma. I was just calling it Magma. And then someone pointed out the computer algebra system. And I said, oh, yeah, okay. That's close enough. They're doing logic, math stuff. Damn it. And then I was like, okay, what's next? And then trying to think of things. I wanted something that felt industrial. Rust, a good name is short and easy to say and easy to remember and easy to Google for. It's embarrassing how much thought has gone into this stupid name.
It's one of the hardest problems in computer science.
Yeah.
There's a conversation I've had today about naming.
Yeah, exactly. Something that's kind of felt industrial. The name Rust is great because it feels like hard and heavy and serious. That's part of the reason it's such a good name. It's part of the reason why the language is so successful. It's mostly because it's awesome, and the borrow checker is amazing, and it's useful.
Yeah, it's just wasn't hobbled by a crappy name.
Exactly. Coke is a terrible name, right? That's obviously a name come up with by French type theoretic, like logician people, which is who came up with it, right? A bunch of French academics. So just like, it's Magma plus ide, because, halide, bromide. It's just like an industrial sounding thing, and Magmide is a thing that no other project has. No other project is called that. So it's like, perfect, fine, good enough. That's the reason.
Well, thank you.
Yeah.